Any questions about anything before we start? I'm going to try to remember that that clock is actually 1 minute fast, which is good at the beginning of class and bad at the end. So anyway. Yes? How was my weekend? It's all right. I didn't go to the football game.
Me neither.
No, I didn't go to the hackathon. I went to the inauguration thing on the art squad, most of it, not all of it, because it was early. But I heard her speech. And then I went up to the ag quad and saw some people from the past who were hanging out. Like Cameron, that guy who came to class that one day, he was there, and a bunch of other people. CTB was nuts on Friday night, as I recall. But I still have my laptop with me, and I was working on the monograph. So, and Sunday, I feel like I got a lot of some cleaning type stuff, right? Yeah, got to take care of the house, you know. Anyway, I didn't get to the lawn though. That was one thing I wanted to do. But if anyone wants a job cutting, no, it's not a big one. Any other questions? Okay. This is first reminder that in 2 weeks-ish, we're going to have a prelim in the Wednesday class. And the people who have Wednesday conflicts, please get in touch with me soon. I'll send out an email about that because I don't want to have it be like the day before somebody says, oh, I forgot to contact you about my Wednesday conflict. So we can make arrangements for those folks. So anyway, we're wrapping up the discrete time, linear time invariant system stuff, and we're going to move on today into continuous time. And so last time, the big sort of focus was on discrete time LTI systems. And our standing assumption is that when H is the system's impulse response, then the input function space is as big as it can possibly be. It's what I call script D sub H, which is the set of all x in f to the z, such that H convolve with x exists, set of all signals convolvable with H. And we saw last time that that was kosher as an input space for an LTI system. It's closed under shifting. It's a subspace. And it contains all the finite duration signals because any H is convolvable with every finite duration signal. And the system mapping is just convolution with H. So the main consequence of this is that the impulse response tells you the whole story about the LTI system. If someone comes up to you on the street and says, here's an H, what system does this go with? You say, well, provided we use the standing assumptions, it's the system whose input function space is D sub H and whose system mapping is H convolved with X, period. Thus, every system property has an embodiment in terms of a property of the impulse response. And that's a big consequence. And the two important system properties that I wanted to talk about are causality and BIBO stability. And we're pretty much done with causality. So we define causality. And causality just means essentially that the present value of the output can depend only on the present and past values of the input and not on the future values of the input. And we saw that the system is causal if and only if h of n is equal to 0 for n less than 0. And I thought, I forgot to write down at the end of class last time where we stopped. And I thought we went over the example systems in terms of causality. And I think maybe we did that just sort of verbally and without my writing anything down, because all the answers are pretty easy. In fact, I know we did, because I remember when I asked you about the shift system, people said, well, sometimes yes, sometimes no. So we did that. Okay, so the last system property I want to talk about is BIBO stability. Okay, so what's that all about? So next is we want to talk about what is called bounded input, bounded output stability. And its abbreviation BIBO is quite standard. Okay, so what's the intuition behind this? The intuition is that if you disturb the input a little bit, then it doesn't disturb the output too much. That's the intuition. If you don't do anything wacko at the input, then nothing wacko happens at the output. That's purely the intuition. Mathematically, what it means is the following. So here's the definition. A system is BIBO stable when the following condition holds. Conditions. First off, every bounded signal is in the input function space X. So every bounded X in f to the z is in the system's input function space. Capital X is an allowable input for the system. And another way of stating that, in terms of our signal spaces, is that L infinity, little l infinity, is a subset of X, in fact, a subspace. And if I take one of those bounded signals and put it into the system, what comes out of the system is also a bounded signal. So S of X is also a bounded signal for any such X. And stating that mathematically is if X is in L infinity, then S of X is also in L infinity. And if you want to get even fancier, you can say that L infinity is a subspace of capital X invariant under the linear mapping S. But we won't go there. Okay, now the key thing, one thing that goes under people's radar is that for a BIBO stable system, the bound on S of X is likely different from the bound on X. Like the system could amplify an input but still keep it bounded, or it could attenuate an input and still keep it bounded. So it's not going to be like an input that's between plus and minus 17 always goes to an output that's between plus and minus 17. It might go to an output that's between plus and minus 17 times 10 to the 59th, but that's still bounded. That's what BIBO stability is. Every system property corresponds with a property of H. What's the property of H to which BIBO stability corresponds? Okay, so here it is. A system with impulse response H is BIBO stable if and only if H is absolutely summable. That is to say, H is an L1 signal. That's the criterion. It's very simple. And the cool thing about having L1 and L infinity around early in the course is that we can get right to the jugular of this property right away. This is something that usually waits for later in a systems type course, but we can go right after this. Okay, so why is this true? Why is this true? I'll show you one direction, and you can look at the monograph for the other direction. Okay, so half of a proof. And I'll refer you to the monograph for the rest. And by the way, like I told you, or maybe I didn't tell you the first day of school, I look favorably upon people who find typos in the monograph. So the more you can send me, the better. And I'll try to remember it down the line. And since I'm trying to work through and finish it this semester, and I'm essentially rewriting all the chapters a little bit, and some of them a lot, I'm especially hoping that the ones that get rewritten a lot, you look at those carefully for typos. You know, and there's this guy a few years ago who just found, you know, infinity over 2 typos. It was crazy. He spotted more double periods and you know, that kind of thing than anybody I thought was humanly possible. And so at the end, I actually gave him like a third of a letter grade higher or something than his score was, because he was so awesome at that. So there are grade points in finding typos. Anyway, here's half of the proof. Suppose H is in L1. Like, okay, if lecture ever gets boring, read the monograph and find typos. That's a good piece of. Okay, so suppose H is in L1. What we want to do is we want to show that the system is BIBO stable. What do we have to do to show the system is BIBO stable? We have to check the 2 conditions. Is every bounded signal in capital X? So the system is BIBO stable because why? Let's take it apart. First off, every bounded signal is in X, and remember, for our system's understanding assumption, it's always the set of all things convolvable H, because why? Why is every bounded signal in the input function space for a system whose impulse response is L1? What's the question we're trying to answer? We're trying to answer why every bounded signal is convolvable with H when H is in L1. Yes, that's what I called it, actually, criterion 3 for convolution existence, which says if I have an L1 signal and an L infinity signal, I can convolve them together, and in fact, I get a bounded signal, and that's the second half of the story. So criterion 3 implies that H convolves with X exists when H is in L1 and X is in L infinity. Why is H convolved with X, which is S of X, also bounded? That's also by criterion 3. The second part of criterion 3 actually put an upper bound on that. And these criteria have different numbers in the monograph, of course, because they're in some chapter. So they're criteria m.n for some n. And m, of course. In fact, the infinity norm of that thing, S of X infinity, that's the sup of all the S of X values, is less than or equal to the 1 norm of H times the infinity norm of X. That proves impulse response absolutely summable implies BIBO stability. The other way around is a little trickier. You can look at the monograph for that. You have to build an H, or you build an input X that if H is not in L1 makes H convolved with X not exist. But whatever. I'm not going to do it in class. All right, now, seeing that last equation there, or inequality, puts a little quantitative meat on what I said a minute ago about the bound on the output and the bound on the input not being necessarily the same. So the last inequality shows that you could have S of x infinity a lot bigger than x infinity, even for a BIBO stable system. And that's going to happen if the one norm of h is big. But if the one norm of h is less than 1, then S of x infinity is always less than x infinity. For all x. So if h norm 1 is 10 to the 59th, that's when you get that 10 to the 59th situation going on, where you put in a teeny input x, and boom, out comes something that has amplitude, so to speak, 10 to the 59th. But still, it's finite. It's bounded between plus and minus 10 to the 59th, so whatever. You don't worry about that. And h sub 1, in some sense here, acts as a system gain, roughly speaking. If you think of every LTI system as being like an amplifier or something, cranking up h sub 1 is like turning the volume knob on the system up higher. Cranking h sub 1 down is like turning the volume knob lower. And on the next homework assignment, which is going to be covered on the prelim, by the way, so we're going to have a little more rigid deadline for that, there's a problem where you actually have to find an input that makes that inequality hold with equality, given a certain h. Okay, so that's BIBO stability in terms of the impulse response. It turns out that a stronger result also holds, and this is useful actually when you're trying to do applications. And I'll just tell you what that is. And I'm not going to prove it, but you know there is a part of a proof again in the monograph, and this even involves a more advanced concept, something from functional analysis called the uniform boundedness theorem, or the Banach-Steinhaus theorem. Okay, so here's a stronger result, stronger BIBO stability result that we won't prove even half of. It goes like this. A system in this context with impulse response h is BIBO stable if and only if every bounded right-sided x is convolvable with h, and for every such x, S of x is also bounded. Now, why is this a stronger result than the original? It's stronger because what it says is that to check for BIBO stability, all we have to do is check that the right-sided signals work in the definition of BIBO stability. And automatically that's going to imply that the left-sided signals work, or the two-sided general bounded signals work. So that's why it's a stronger result. And to explain why mathematically you need the heavy artillery to prove it, it's sort of beyond the scope of this class, but I can talk to you about it in private sometime if you want. Okay? All right, so Any questions about this stuff? This is the end of general discrete time LTI systems for now. Later on, of course, we'll come back to it. We talk about DTFTs and Z transforms and transfer functions and all that sort of thing. Any questions? Yeah, David.
The S of X, why is it less than or equal to?
Well, that's if you look at criterion 3, this is exactly what it says. It says if you have an L1 signal and an L infinity signal, their convolution exists and is bounded, and its infinity norm satisfies the inequality. It's less than or equal to the product of the L1 signal's L1 norm and the L infinity signal's L infinity norm. It's just the way it is. Any other questions? About the discrete time signals, systems, whatever? Stuff you wish you had seen that you didn't? No? Yeah, Ricardo.
Are we ever going to convolve images?
In this class? No, I don't think so. You don't look too crestfallen. But you're always smiling, so, whatever. Okay. No, I think that if ECE 4250 were being offered next semester, which almost certainly it's not because Professor Chen is on leave, you would convolve images there. In what? Oh, also Professor Johnson's class on signal processing applied to painting analysis. According to Erica, they do it there. Yes?
This goes back to your past lecture, and you said something like the X2 norm is the infinite dimensional version of the Euclidean norm.
Yes.
Finite dimensional.
Mm-hmm.
Because I didn't really understand that.
Okay.
I'm not sure if this is relevant.
No, it's fine. Which is this easier for you to see than that one?
I just don't understand this.
No, I'm talking about the board.
Oh no! Oh, it's good.
Okay.
Yeah.
In Rn, say, the Euclidean norm, and in fact this works in Cn as well, so I'll just say Fn. If you take x, I'm going to call it the 2 norm, it's going to be the sum from j equals 1 to n of xj magnitude squared, all raised to the 1/2. The square root of the sum of the squares of the entries in the vector. Okay, this is the set of all n-dimensional column vectors with components in F equals R or C. That's what the Euclidean norm is. Okay? Now, in L2, the 2 norm, yeah, exactly. X2 equals the sum from n equals minus infinity to infinity of, and let's use m here because I use m for a dimension up here, x of m magnitude squared. All that to the 1/2. So this is just the infinite dimensional generalization of the Euclidean norm in n-dimensional space. Fair enough?
But do we have to know what Euclidean norm is? Because that just didn't click to me.
What do you mean by do we have to know what Euclidean?
I don't know. It's just when you said that, it just kind of blew away.
What if someone comes up to you on Hope Plaza with a weapon, and says, I forget the name of the Euclidean norm. No, you could stall. You could pretend like you don't speak English or something. I had a Swedish friend who was a grad student here. This friend of mine who was a grad student in ECE from Sweden, every time he got stopped on the highway for speeding, which was frequently because he drove really fast, he would pretend he couldn't speak English. I don't, And they would let him go. And he is now, by the way, I just for the heck of it, just a couple of weeks ago, I thought of him because he's a really cool guy. And so I Googled his name. And it turns out he's like the vice president of Ericsson Electronics now for Asia Pacific. So he does all China, all Indonesia, all that stuff. major, major market for Ericsson Electronics. Ericsson is like the biggest company in Sweden. So, you know, that's what you can do if you get a PhD in EC at Cornell and pretend you can't speak English on the highway. Right? So, all right, any other questions about the discrete time stuff? Okay, so let's move on. And when we talk about the continuous time analogs of all the discrete time stuff, it's going to look a lot alike. And therefore, I'm going to charge through it and punt more stuff than usual to the monograph because everything looks so similar to stuff you've seen already. The difference is that we have to be a little more careful. In fact, a lot more careful when we're dealing with continuous time stuff because unlike discrete time signals, lots of analytical weirdness can crop up in continuous time. And the kind of weirdness that can crop up generally is the stuff we want to sort of wish away by making appropriate assumptions on the signals we're dealing with, which we will, but there's some analytical weirdness stuff that we can't wish away. It's an unfortunate consequence of continuous time. So what we're going to do now is, first we're going to talk about continuous time signals and stuff you can do with them. Specifically convolution. And then we're going to move on to continuous time LTI systems, and the definitions are going to look very similar, but there's going to be some notable differences that I'll try to draw attention to as we get to them. All right, so first off, what we want to do is we want to restrict our attention to signals that are reasonable, that aren't really nasty. Okay, so first order of business, what we're going to do is we're going to define a useful class of signals that aren't pathological. And this class of signals is plenty big to satisfy anybody's needs in applications. So this is plenty general for applications. And first, I've debated how to go after this, whether to talk about pathology first and then talk about defining it away, or whether to give you the definition and then talk about the pathologies that the definition avoids. And I decided on the latter. So let me just give you the definition first. And of course, the background to all of this is that time is a real variable now. So the real numbers instead of the integers are modeled for continuous time. And a continuous time signal with values in f equals r or c So continuous time f valued signal is a mapping. And again, we're just going to use the notation little x, y, w, all those from R this time into f. And guess what we call the set of all continuous time signals? It's going to be f to the r instead of f to the z. So that's to get halfway to first base. That's what continuous time signals are. And of course, just like a discrete time, we have structure on f to the r. So as in discrete time, f to the r has a vector space structure and we do it just the same way as we do it in discrete time, except everywhere you saw an n or an n in the integers, you see a t, or a t in the reals. So just let me just say this one particular one. I'll write it out. If x1 and x2 are in f to the r, and c1 and c2 in f, then the signal x equals c1 x1 plus c2 x2 has specification x of t is equal to c1 x1 of t plus c2 x2 of t for all t in the reals. So you can see it's a straight up substitution of t for n and r for z. And we also have accompanying notions of that's a new noise. Isn't it? That sort of buzzing sound for the middle board. The front board has the cataclysmic pre-volcano sound. Occurs every now and then, but so we also have time shifting, and again for t0 in the reals and x in f to the r, shift t0 of x has specification this. Okay, so we have that, just like we did in discrete time. Everything is identical up to now as in discrete time with the substitutions where they're supposed to happen. All right, now for the definition of the non-pathological signals. And this terminology is not something you should share with your math professor if you're taking a math class, or even with other engineering professors, because it's sort of private to this course. But it's convenient to have a one-word thing we can use. So here's the definition. X in f to the r is what we call a decent signal. Sorry, but I mean it's a reasonable word. We could say non-pathological, whatever. When it satisfies the following three stipulations. And remember, I'm giving you the definition first, and then tell you what pathologies we avoid. First off, X is continuous except possibly for jumps. Now, you may say, well, wait. Doesn't continuous mean it doesn't jump? Well, you'll see something worse. So X is continuous except possibly for jumps. And we want to allow jumps because there's some useful signals out there that have jumps in them, like a square wave. A square wave is a very useful signal, right? And in fact, a square wave has infinitely many jumps. Doesn't, you know, so we even want to allow signals that have infinitely many jumps. But we don't want to allow anything worse than a jump as far as discontinuity goes. And I'll get to one of those in a second. Second thing is that X has, at most, finitely many jumps in any bounded time interval. So like between time 0 and 1, you can't have a signal that has infinitely many jumps in it. And we can actually construct one of those pretty easily. And finally, this is the most reasonable assumption. X is bounded on any bounded time interval. Okay. Those are the three assumptions for decent signal. And it's very close to what a mathematician would call a piecewise continuous signal, but it's not quite exactly the same. All right, so just to make sure you believe that these assumptions rule something out, so respectively, the assumptions rule out the following kinds of pathologies. First assumption, that X is continuous except possibly for jumps. Here's a horrible signal. X has specification X of t is equal to 1 when t is irrational and 0 when t is rational. Okay, that is a really awful signal, one that you will never encounter in applications. It's a bounded signal. That's a good thing about it. But it's not even jump discontinuous because there's so many rationals and irrationals. The jumps are, if you want to even call them that, are dense in any bounded interval. Okay? So that is what the first assumption rules out. Second assumption rules out this kind of an X. This X is going to have jumps, but it's going to have infinitely many in some bounded interval. So what this signal has specification X of t is equal to 0 when t is less than 0, and 1 when t is bigger than or equal to 1, or t. Let's do it this way: t is bigger than 1. No, and it's equal to 1 when t is between 1 over n plus 1 and 1 over n, where n is odd, and it's equal to 0 when t is in this interval and n is even. Okay, this is another bounded signal. Just like the first one, it takes on only 0 and 1 as its possible values. Furthermore, it is discontinuous, but it has jumps. And the reason it has so many is that it looks kind of like this. Like if this is t equals 1 out here, this is going to be t equals 1/2, and then down to 1/3, it's going to be 0, and then from 1/3 to 1/4, it's going to be 1, then from 1/4 to 1/8, it's going to be 0, then from 1/8 to 1/16, it's going to, you know. So it has infinitely many of these like chimney type things converging on 0 of ever narrower widths. So that's the kind of a signal that the second assumption rules out. And finally, the third assumption rules out this kind of a signal. X of t is equal to, how about 1 over t when t is positive, or let's just make it when t is bigger than 0. 0 when t equals 0, and minus 1 over t when t is less than 0. And this one is decent enough, even though it isn't decent, that we can actually graph it. Looks like this. And its value is defined to be 0 at time 0. But this signal is unbounded on any bounded interval containing 0. Therefore, it fails the third test. OK, so these are the signals we're trying to rule out. And that's what decent signals do. OK. So generally, we're going to confine our attention to decent signals, but I will always try to say decent when we're assuming it and tell you when the result of something comes out to be decent or when it doesn't necessarily, because there are instances of that as we go along. So we're going to have a lot of results that say if x1 and x2 are two decent right-sided signals, then their convolution exists and is decent, you know, that kind of thing. We'll be seeing stuff like that. OK, so what else do we have in continuous time similar to discrete time? We have this vector space structure. We have the time shifting. Question. Is the set of decent signals a subspace of f to the r? How many people think yes? If I take the sum of two decent signals, I get a decent signal. How many people? Come on, David, you look tentative back there. How many people think no, sometimes it's not? Maybe. Nobody thinks that. Well, the ones who voted are right. It is. Set of decent signals is a subspace of f to the r. And is it closed under shifting? How many people think yes? How many people think maybe not? If I shift a signal that has these properties, you can't take something that's continuous except possibly for jumps and get something horrible like that. Or shift something that has finitely many jumps in any bounded interval and get a signal that has infinitely many in some. Or that. So, fact. And by the way, I'm not even going to make up a notation for a set of all decent signals. So the set of decent signals is a subspace of f to the r that's closed under shifting. So it's a good thing to have those properties for a set of signals, just as it was in discrete time. We saw time and again. What other closed under shifting subspaces did we have in discrete time? What's an example of a closed under shifting subspace we encountered relatively early when we're talking about discrete time signals? Right-sided, yeah, very good. Right-sided, left-sided, finite duration. And the definitions of continuous time are essentially exactly the same. I'm not even going to write them down. And again, they just substitute t's for n's and r's for z's and s's for m's, all that. So as in discrete time, we have right-sided and left-sided. And we also have finite duration signals. And you can define finite duration, again, as being both right and left-sided, same as in discrete time. And again, these are subspaces. Each of these sets of signals forms a subspace. Of f to the r that are closed, that's closed under shifting. And also, if you want to go even one step deeper into the whatever you call it, hierarchy or whatever, the set of all decent right-sided signals, the set of all decent left-sided signals, and the set of all decent finite duration signals, each of those is a subspace of f to the r closed under shifting. All right, so far so good. Now's a good time to take the 3-minute break, and then we can talk about continuous time convolution and related results. First, we'll do analytical properties of signals. No, it's like it always has to have a value coming in from the left, a value coming in from the right, and then it could be anything at that point. So these count as jumps for me. Anywhere. That counts as a jump. Anything that has a limit from the right and a limit from the left.
Right. Then I don't get why the first signal that we have, the one where it's
Irrational.
yeah, the rational and irrational.
It doesn't have a limit from the right or a limit from the left, because every time I move along the real number axis, I hit infinitely many zeros and ones along the way to anywhere. So it can't converge to 1 or to 0 from the right or the left.
So if there's like many jumps, is that considered not decent?
No, a square wave has infinitely many jumps.
Right.
But that signal doesn't even have jumps. It's a worse kind of discontinuity. It's a sort of fatal signal error or something. I don't know.
Like, what would this signal look like? I mean, for every
Your guess is as good as mine.
Huh?
You can't graph it. No one can. Maybe someone who lives in a higher dimension.
Oh, wait. So like, I mean, the way I see it is like there's like a series of real numbers, and then there's like once in a while there's irrational numbers.
No. The rationals and the irrationals are both dense. Like, it's not. Neither of them is once in a while.
Oh, really?
Yeah, this is a once in a while. This one.
Right.
But no, not the rationals and irrationals.
Wait, so is it like irrational, rational, irrational?
No. It turns out that there are a lot more irrationals than rationals.
Like irrational numbers are like everywhere.
Yeah, but so are rationals as well. They're also dense. But the rationals have what they call measure zero. Yeah, that's a signal you don't even want to think too hard about, because.
Right. I mean, it's just like I was thinking about it. The way I saw it was like there's like a lot of rational numbers for this time frame, and then there's like irrational here, and then rational for a long duration.
No, you can't even go 10 to the minus 59th without hitting both a rational and an irrational.
Oh, okay.
Yeah. Yeah, that one is kind of like there was this movie, I forget the title, where people's heads exploded.
Wait, what?
Where people's heads exploded all of a sudden. This movie, I forget the name of it. Some people had psychokinetic powers and they could make people's heads explode on stage.
There's a movie where a tire goes around and makes living things explode.
Yeah. All right.
Oh, that's on Netflix. Yeah, it's on Netflix. It's rubber. Did you actually watch it? Oh, I've seen it multiple times.
No wonder. All right, so anyway, so far so good. We've got these algebraic properties of signals, right and left-sided and finite duration, and we also have the notion of decent signals, and we have a lot of subspaces floating around that are closed under shifting. Now let's talk about analytical properties. And of course, decency is an analytical property or a set thereof, but I'm calling these analytical properties in analogy with what we did in discrete time. And these are going to be things like bounded, etc. So we're going to have, just as we did in discrete time, we're going to have some L infinity, L1, L2, all that kind of stuff. Okay. Before we talk about these properties, I want to mention that, as you probably guess, integration plays a role in continuous time that summation plays in discrete time. So here's a little short aside. In what follows, we're going to be seeing integration. So in continuous time, plays the role of summation in discrete time. Okay, but the difficulty is that there are numerous different notions of integration. Everybody agrees about summation, right? But there are different ways of defining integrals. So, and specifically, there's two ways of defining integrals that are kind of in conflict. So we can define integral in different ways. And the two main ways are, the first way you learned, like in Calc 1, in high school or first year of college, is what's called a Riemann integral. And the Riemann integral, what you do is you take a function and you make a little staircase approximation, and then you add up the areas of the stairs, and then you make the stairs get narrower, 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 and take the limit, and that's the integral. And by the way, over the course of the semester, we'll see numerous things where there's a German thing and a French thing. Okay? And the German things tend to be more discrete, and the French things tend to be more effusive than continental. You know, like I don't know, like French literary theory or something. So this is Riemann. This is the German kind of integral. And the other one is the French version, Lebesgue. And by the way, Lebesgue, the first letter of Lebesgue's name, that's where L comes from in the L1, L2, L infinity. It's his fault. Yeah, Riemann lived a while ago. Lebesgue was actually active around the early 20th century, you know, so he's a more recent guy. And the Lebesgue integral is based on something called measure theory. And measure theory is way cool. Measure theory, if you want to do probability rigorously, that's the way to go, okay? And I wish we could do 3100 that way, but no, you know, you can't. If you want to learn Lebesgue integration and measure theory, take Math 4130. Okay, strongly recommend it. But anyway, it turns out that a really good thing about decent signals is that those two notions of integration coincide. So it turns out these work out to be the same for decent signals. So it's sort of like, phew, we don't have to worry, you know, about sort of Riemann-Lebesgue issues. I will allude to Riemann-Lebesgue issues later on when we talk about things like orthogonal expansion and Fourier series. But just for straightforward integration, we don't have to worry about the difference between Riemann and Lebesgue. But we're not out of the woods on that. So I'll tell you sort of a cautionary thing. The difference crops up in other ways. Okay, so we're going to see integrals. And so we don't have to say this is a Lebesgue integral, this is a Riemann integral, because all the signals we'll be talking about are decent signals. Okay, that's one thing. Another thing is that all those nice results about, absolutely summable implies summable in discrete time, same thing works in continuous time. And just that one particular result is good to know, so let me just state it. Well, we'll wait till we get to L1. Okay, so let's move on. Now that we have that integration aside taken care of. A signal is bounded and again, it's essentially the same definition. When there exists a positive number R such that the absolute value or magnitude of x of t is less than or equal to R for all t's. Okay, now, for decent signals, this turns out to be the same definition as what we call Lebesgue bounded. Lebesgue bounded things are things that are bounded almost everywhere. That's how weird it gets. Like you could have a signal that's, I'll get to you in a second, that's equal to 0 for all t except at t equals 0 where it's equal to infinity. And a Lebesgue person would call that an essentially bounded signal, a signal that's bounded except for a set of measure 0. But we're not going to go there. We don't have to worry about that. We have this simple definition for bounded.
You wrote a signal f in f to the z?
F to the r, yes, thank you. Sound like you've been through this before. Yeah, I will do that occasionally, by the way. I'll sort of collapse into discrete time once in a while when I mean to stay continuous. That's what it means for a signal to be bounded. And L infinity, capital L now, is the set of all bounded x in f to the z. Or f to the r. See? Told you. All right. And we could say it's a set of all bounded decent signals in f to the r, but I'm not going to sweat that detail. Is L infinity a subspace of f to the r? Is it closed under shifting? One of these days, it's not going to be a subspace and or not going to be closed under shifting. And you'll all be sorry for riding the caboose all this time. While all the heavy lifting gets done. No, okay, so L infinity is a subspace of f to the r closed under shifting. Okay. L1, absolutely integrable signals. So a signal x in f to the r is absolutely integrable when the integral from minus infinity to infinity of the absolute value or magnitude of x of t dt exists. Okay, now signals in f to the r don't necessarily have integrals even in the Lebesgue sense. They may fail to be integral in the Riemann sense or the Lebesgue sense. It turns out that that horrible rational irrational one is not Riemann integrable, but is Lebesgue integrable, and it integrates to 1 Lebesgue. I always thought that was kind of interesting. But like I said, in the back of our minds, we're always thinking we only care about decent signals. So when you look at that, think of X as being a decent signal. Even though I'm not defining L1, the set of all absolutely integrable signals, to be the set of all decent signals for which that exists. L1 is the set of all these. Again, L1 is a subspace. Of F to the Z, F to the R, C. Can't get out of the habit. Closed under shifting. And as in discrete time, we have norms on these L spaces. And again, the norm is just a notion of size. How big is a signal? Or if you take the norm of the difference, it's a notion of distance between two signals. That's the intuition behind norms. So we have norms as in discrete time. On L infinity, you have the infinity norm, x sub infinity, and you can probably guess it's just the sup of all the x of t values, magnitudes, such that t is in the reals. So again, a straightforward substitution of t for n, r for z, and x1 for, this is true for all x in L infinity, and x sub 1 norm is just going to be that integral over there. And that's for x in L1. All right, now comes the first sort of really annoying thing about continuous time. Remember back in discrete time, like 2 weeks ago, or a week and a half ago or so, we had this nice containment. Like, if you have a signal that's absolutely summable, then it certainly has to be a bounded signal, right? But in continuous time, that's not the case. You can have something that's absolutely integrable. I mean, admittedly, it can look pretty ugly, and the example I give in the monograph is pretty ugly, but not bounded. So, in discrete time we had little L1 subset of little L infinity. It's not true that big L1 is a subset of big L infinity. And it doesn't go the other way around, obviously, because the constant function 1 is an L infinity, and clearly that's not absolutely integrable. They have a non-trivial intersection, and they have stuff outside of each other. And there's an example of this in the monograph. And just to describe what it looks like, I actually use it for several different things. It's a signal that that has, like, it has little, it's symmetric about 0, and it has little blocks like that get taller and narrower as you go out. Okay? Dot, dot, dot. Same thing over here. So it's like infinitely many chimneys that get narrower as you go out toward infinity and taller. And so clearly that thing is not bounded because it goes up and up and up in terms of its peaks. But if you choose the heights and the widths just right, you get something that has a finite area under it. And that'll be an L1 signal. And it's not an L infinity. And if someone could think of a clever name for that so I could call it that in the monograph and refer back to it, that would be cool. You know, I can't. I'm not good at thinking of clever names. There was a really cool article in the New York Times this summer about, or last spring, about product naming as a career. Like, there's an actual career of being someone who names products. You know, you get paid. Sometimes you contract your services out. Sometimes you work for a company. And it was about the life of such a person. So imagine that. If you had to come up with the name Slinky, or, yeah, David.
I just have a question. You mentioned that there was the meg sum, or you could integrate it's all 0 except that
Yeah.
0 is infinity. Is that?
Oh, no, not that one.
You can't do that?
No, not that one, but the one with the rational, irrational.
Oh.
Yeah.
I was just wondering, where was the approach to, like, how you get that without getting into the details? Like,
Okay, here it is step by step. Number 1, a point has measure 0. Number 2, the countable union of any set of sets of measure 0 has measure 0. So the union of all the rationals, that has measure 0. Point number 3, if you have a set of measure 0, that's measurable, and therefore its complement is measurable. Therefore, anything that's constant on a measurable set has value equal to the value on that measurable set times the measure of that measurable set. In this case, that measurable set is the irrationals. See, that's the details, unfortunately.
it almost makes sense.
It almost... Look, I told you, it's French. All right? Nothing against the French. But, you know, obviously I have French ancestors, right? On my father's side. Okay. What's that? No? Do you have any French ancestors? No. All right. Okay. All right, L1 is not a subset of L infinity, unfortunately. That makes things hard sometimes. And we also have L2. So we also have L2, the set of square integrable signals in f to the r, i.e. those for which the integral over all t of the magnitude squared of x of t exists. And it's also a subspace of f to the r. It's also closed under shifting. And the 2 norm is the uncountably infinite version of the Euclidean norm to make your life even worse for today. It's x sub 2 norm is the integral from minus infinity to infinity of the magnitude squared of x of t dt, all that raised to the 1/2. And that's for x in L2. And L1 is not a subset of L2. L2 is not a subset of L1. They do intersect. L2 is not a subset of L infinity. So, and no nice, quote unquote, nice containment relations between L1, L2, and L infinity. Unlike discrete time. Okay, so there we are. We have analytical properties now. In addition to decency, or decentness, we have bounded, absolutely summable, square summable. Those are important sets of signals, come up in applications a lot. Or integrable. And by the way, like, now that we're in continuous time, we can sort of talk about voltages and currents and things like that a little bit. You know, we can try to draw ECE analogs to various things. You might have heard the expression, I don't know if you heard this in EC 2100, that, you know, there's something called like a power type signal or an energy type signal. You've heard that kind of thing? Yeah, an energy type signal is an L2 signal, basically. That's what it is. It's an energy type signal. It's a signal that has finite energy. A power type signal is like a periodic signal because it has finite energy per unit time kind of thing. Like you look at a piece of it and it has that integral existing. Fair enough? The 2 norm of over a period of a power type signal has a name. Does anyone know what that name is that an ECE would call it? Manish. The RMS value. Okay, why do they call it that? It's the root mean square. Okay, and the mean comes in because you're taking 1 over the length of a period. So anyway, all these things have nice ECE kind of embodiments, right? Okay, so we're not just blowing smoke. We're talking about real stuff here. All right, now it's time to move on to convolution, and I have just enough time to give you the definition. So on to convolution. Here's a definition. For x1, let's state it this way. Given x1 and x2 in f to the r, their convolution, if it exists, and again, we're going to have times when it does, times when it doesn't, is the signal x in f to the r with specification, or I'm not even going to give it a name. I'm going to call it x1 convolved with x2 right off the top. x1 convolved with x2 in f to the r with specification x1 convolved with x2 of t. So again, we've got this whole signal and its value at time t equals integral from minus infinity to infinity x1 of tau x2 of t minus tau d tau for all t in the reals. And again, if you pick an arbitrary x1 or x2 from f to the r, you might not even be able to compute that integral in the Riemann or the Lebesgue sense. But we're always in the back of our mind, again, thinking decent signals. And for decent signals, this always makes sense to try to compute this integral. And how one interprets the integral as a Riemann or Lebesgue doesn't matter, because those two notions coincide. I feel as if I'm beating a dead horse, but whatever. It won't hurt the horse anymore. Right? So, it's not 4:10 yet, it's 4:09 because that clock is 1 minute slow, or fast, remember? Okay, so we'll pick it up next time.